Okay, so now I'm recording. We're going over the quiz on question 2. So the radius is just going to be the height of your rectangle at any point in that region, which in this case, the height of the rectangle is controlled by the square root of x. Y is whatever the square root of x is. So depending on where we are, that's going to be our radius. Of course, our radius squared at that point would just be x. So your options on the quiz, well, let's set this up first, and then you can kind of compare it to your options. Since we're talking about a dx integral, remember we're talking about what's happening with that region on the x-axis. So x is going from 0 to 3. Don't forget your pi at the beginning of your integral, and then you're taking r of x squared. So I wrote this trying to like leave it unsimplified. I know we normally simplify this, but I wanted it to be really obvious by looking at it. If you could kind of compare this with what you were doing, with what the answer would be, without having to sit there and be like, oh gosh, how do I rewrite this in the form that she has? So I just left it unsimplified so that it would hopefully poke out at you a little bit more. It would be the square root of x squared dx. And that, yeah, so again, I don't know what option it is for you, but I put in some options there with y. And then I put in an option where r of x was not squared, just trying to see if somebody forgot about it. I know I was tricky. Sorry. It happens. Sometimes I get a little tricky. But I mean, distractors would be pointless if I didn't think they were things that you might choose, right? Okay. So that was number 2. And I'm guessing that one probably went a little better also just because it was a disc. Number 3, since I already have the region here, I'll just keep going on this one. So number 3 was find the region bounded by y equals the square root of x, y equals 0, and x equals, for this region with x equals 3. So same exact region. Choose the correct setup to find the volume when the region is revolved about the y-axis. So everything is the same in this instance, except now for number 3, we're revolving it about y. Now, when you revolve this region about the y-axis, suddenly you're not dealing with a simple disk situation anymore. Now you're looking at a washer. If you can imagine taking this region and spinning it around the y-axis, you would be able to see that it would form this, I mean, it would look like a cylinder really, but the inside of it would definitely not be touching the axis of revolution at every point. It would only be touching here at the bottom. That's how you know it's a washer, because it's going to have all this empty space in the middle, and it's only going to be filled out on the edges, all the way on the bottom, but on the top you'd have a bunch of empty space. So this is definitely a washer. So you're going to be looking for a couple different things here. You're going to be looking for an outer radius and an inner radius. And then we need to remember that because we're revolving about a vertical axis of revolution, for a vertical axis of revolution, everything needs to be written in terms of y. So we're going to be following the form pi times the integral from c to d of big R of y squared. If it drives you crazy to have to use that many grouping symbols, you can write it as, you know, kind of like we do with sine squared and cosine squared, and you can put the square inside there. You can tell it's been driving me crazy because I'm switching it up a little bit here. So you're going to take the outer radius minus the inner radius. Each one of those is going to be squared, and then you're going to integrate with respect to y. Okay, so this is with respect to the y-axis. And I already marked this here. So notice that your region is going from y equals 0 up to y equals the square root of 3. So those are going to be the values you're using for C and D. Now you just need to figure out your outer and inner radii. And that's the hard part here. Sometimes it's hard just to realize when we have a disc or a washer. But if you feel like, okay, I understand that it's a washer, I'm just not sure how to find the radii. Well, let me walk you through this one. Remember that to find the outer radius, we're looking at this region from the axis of revolution all the way to the outer edge. Now, the nice thing about this, and you might have seen one on your homework that didn't have this situation, but the nice thing about this is that the outer edge of this is vertical. Oh, you would not have learned about discs and washers in Calc 1, Zane. If you want to learn more about it, the only thing you're looking at is the asynchronous video that I posted on Friday. So yeah, this is new material for you. So we all should have watched the lecture that I posted Friday. I don't know when you watched it. Now I'm scared and I'm going to go check my views, but I'm sure if it wasn't up there, someone would have told me. Which there's my account. Oh, I opened up YouTube and it was my husband's account. It was nothing but like the weekend videos, and my kids are like obsessed with the weekend. It's insane. Okay, asynchronous week 2. Looking at my views now. 28. Excellent, because there are like 17 of you. Okay, good. Everything's fine. Sometimes I panic and I'm like, what if I accidentally forgot to upload it? But someone would have told me. Okay. All right. So let's talk about the outer radius. Because we have a nice straight edge on our outer edge, that's good. It's also kind of nice that we're working with an axis of revolution that is the y-axis. Anytime you're not working with any like translated line, as long as you're working on one of the main axes, that makes life a little bit easier. But if you can sort of visualize how you're moving from the axis of revolution all the way to the outer edge, and I don't want to put an arrow on this yet because I don't want to show this heading to the right. I know we always think in terms of left to right, but remember we're always thinking in terms of y, we're thinking right minus left. So when you're moving from the right to the left, you're always moving towards the axis of revolution, but you're going to start at the furthest rightmost place on your region, which in our case is this line x equals 3. And then you're going to move to the left until you hit your axis of revolution. And that's how you're going to get big R of y. So big R of y is going to be right minus left. Left in this case is always going to be your axis of revolution. We're taking 3 minus 0, which is 3. And check this with just sort of your understanding of what's happening visually with this figure once you rotate it around that axis. You can see how when you start to spin this around the y-axis, the outer edge is always going to be 3 units away at every point. And I feel like that's a little bit more intuitive when you have this straight edge. And especially for an outer radius, I think it makes more sense. It's the inner radius that tends to give people a little bit more trouble. When you're looking for the inner radius, a very common mistake is to be thinking like, okay, well, right minus left, and then you start from the outer edge and go up to your function. Remember, this is not the inner radius. This is on your region. When you're looking for the inner radius, you're looking for the radius with that empty space in it. So what you're looking for really is what happens as you move from right to left from the next innermost place to the axis of revolution. And this is going to give you that little function R of y. That's where you've got that hole that's been created. What you're really trying to do here is you're taking the volume of this whole cylinder, but then you have to account for the fact that there's this big empty space in the middle, and you have to take off the volume of the missing chunk. That's what we're doing here when we're taking big R squared minus little r squared. You're just taking that entire volume and then just removing the volume of the empty space. So little r of y is going to go from your function on the right and then on the left to x equals 0. Now, your function right now is written in terms of x. You want to rewrite that in terms of y, and you'll do that by squaring both sides. So if the square root of x equals y, then square both sides, and you get x equals y squared. Sorry. So what we're doing now, when we're looking at that inner radius, is we're moving from the curve x equals y squared over to the left to the line x equals 0, which is your y-axis, or your axis of revolution in this case. So our inner radius is going to be y squared minus 0, which is y squared. So when you put this into the formula here, you're taking big R of y squared, which is going to be 3 squared, minus little r of y squared. Well, if little r of y is y squared, well, now you're going to square that quantity. And again, I really didn't feel that the most important thing here was whether or not you could do the algebra and integrate, even though, yes, technically you can't solve the problem if you don't know how to do that. The new stuff here is all in the setup, and that's what I wanted to make sure you knew how to do. So this was number 3. Are there any questions about why it's a washer, or how I found the outer or the inner radius, or how I found my limits of integration, or why I chose to integrate with respect to y, or any of those things? I noticed, by the way, that some of you, I know I have one more to do here. Some of you didn't really get going on the homework until like yesterday. That's not good, but if you need an extension, it's not a big deal. I can extend the homework for you initially. I know that sometimes it just takes us a while to kind of figure out what is achieved, where do I find it, how do I get started. If it took you kind of a while to get started, you weren't sure what was going on, first of all, always email me if you're not sure about something. Don't delay, because now you're going to have more new material tonight, and I just don't want you to be behind. That's why really I need you to stay on pace. Otherwise, if you get behind, you're going to get really overwhelmed and you might never catch up again. I know that sounds really ominous, and I don't mean to be negative like that, but it happens in Calc 2 a lot. People get behind and then it's very, very hard to catch up. If you need an extension, I don't mind granting it. Just keep in mind that you're going to have more homework that I'm going to be assigning tonight. The only good thing is, that reminds me of one more thing. I was talking with a student over email this weekend, and I kind of came to the conclusion after talking with her that it made more sense to make your asynchronous homework due Fridays instead of Wednesdays. So instead of having 2 sections of homework due today, you only had the 6-1 homework due today, which is what we covered last Wednesday. But the asynchronous stuff that you should have watched at some point between today and last Wednesday will be due Friday. So if you haven't gotten all that finished, you have till Friday. If you haven't started on it yet, you need to get started soon. The only benefit to not starting it yet is that when I teach you the method of shells tonight, you will technically be able to use either method on your 6-2 and 6-3 homework, because they're the same concept. They're both finding volumes, just using 2 different methods. So normally you wouldn't be able to do that using, having the same concept covered in 2 sections, but that's kind of the way it is with these 2 volume sections. You can do a lot of these problems using either method. So if you haven't finished the 6-2 homework, I can't stop you from using 6-3 methods on those problems if you should choose to do so. I, of course, will mention this as I get into 6-3, but I'm not going to force you to use a specific method on your exam. I'm just going to say find the volume, and you're going to use the method that makes the most sense to you. Okay, that being said, I'm going to do number 4. Are there any questions about that? Sorry, I'm like dinging away here. Okay. Number 4. You know what? Well, I'll just redraw the figure. So for number 4, we're using the same figure. This time we're going to revolve this about the line. I believe it is x equals 6. Let me see. It's timed me out. Oh, I had to preview the quiz for some reason, and it timed me out. It said I didn't finish in time.
Yeah, it's x equals 6.
Okay, x equals 6. All right. And I guess I could re-preview it anyway, but okay. Number 4. And by the way, I do not mind going over this quiz because I know that this material is tricky. And I really want to make sure we solidify this stuff. All right, so we're looking again at y equals the square root of x, y equals 0, x equals 3, and this time we're revolving about the line x equals 6. Get to it on here. There it is. All right, about the line x equals 6. So your region, again, looks like this. At 3, you've got this point at 3, square root 3. This is y equals the square root of x, also known as x equals y squared. Now, I labeled this in a terrible place because we're going to need to put our axis of revolution here. Since it's a vertical axis of revolution, I'm just going to write this as x equals y squared, not even worry about writing the other variation of it, which is up here. Maybe 6 is about right there. Okay, so now our axis of revolution has shifted. So when we talk about now taking the volume of this region, as we rotate this region about the line x equals 6, you're looking at a much different situation than you were when we revolved about the y-axis. Because in this case, even though we still have a vertical axis of revolution and we still have a washer, in this instance, we're going to have a shape that looks almost like a donut. If you were to sort of imagine what it would look like on both sides. It's a very crude recreation of this situation here. But this would be basically a circle. It would look kind of like a donut if you wanted to think about it like that. So even though it looks like, wait a second, it's not connected, remember you're spinning it around this whole region. So it's going to come out towards you and then back here and then into the page and then back around. So it's kind of donut shaped. Now, again, we're going to be looking at this formula where we're taking pi times the integral from c to d. And because we have a vertical axis of revolution, everything needs to be written in terms of y. So I'm going to take big R squared of y minus little r squared of y dy. Now, I hope you have really good notes, and you might want to make yourself a summary page for when you take your exam, because we're going to change a lot of this around today when we talk about shells. So for right now, a vertical axis of revolution means we're integrating with respect to y. We're going to change that today. So if you need to make yourself some really good notes and make sure that you understand the differences between the two methods, you'll probably find that helpful on your exam. Make yourself like a cheat sheet, because your exam will be open notes. So make sure you have everything organized in a way that makes it easy for you to piece everything back together again. All right, so let's look first at your outer radius. That's the big radius, big R. Some of you, if you're thinking about this in terms of the smaller radius, you can do that first. It doesn't matter what order they're in. I just like to be consistent all the time. So when we're looking at our outer radius, we're thinking about this in terms of right minus left. And remember, I always want to use my axis of revolution as one of those focal points. So when you're thinking right minus left, don't start here at 3 and go left to the edge, because that's not going to help you. You're looking at the radius, and the radius is controlled by how far away you are from the axis of revolution. So your outer radius is going to go from the axis of revolution all the way to the outermost edge of the region. So remember, you're going right to left, starting at the axis of revolution in this case, because it's further to the right than the edge is, and then move all the way left until you hit the edge of the region. And that'll give you your larger radius, big R of Y. So big R of Y, right to left, is going to be, you have x equals 6 and x equals y squared. So you're taking 6 minus y squared. So right minus left. And then your inner radius, your little r of y, is going to do the same thing. Remember, you're starting at your axis of revolution in this case because it's to the right of your region. And then you're moving to the left towards the innermost edge of the region, not the outermost. So your little radius is going to go from x equals 6 to this line, x equals 3. And notice this isn't controlled by any sort of a variable function. This is just a straight line. It's going to be the same distance away all the time. So we're going to say this is 6 minus 3, which is 3. And our limits of integration aren't going to change in this case. Comparing this to what we did in number 3, we're still taking y from 0 to the square root of 3. That's as high as our region's going to go. So we're going to take big R and square it and subtract off little r squared dy. So I gave you a plethora of options here. I think one of the options I put on here used right minus left as, oh no, I didn't. I did it in the opposite order. Oh well, it's trying to be tricky. But either way, this is the setup for your volume. Okay, questions on number 4? Okay, now today I'm going to talk about the method of cylindrical shells. And I know that sometimes in math, students don't like when I switch the method. They're just like, wait a second, no, I was just getting the hang of this, and now you're going to change it on me, and I don't like that. First of all, it's a required thing that I teach you. It's not really an option to not learn shells. Second of all, you're going to find that sometimes you're going to have to switch your method because you might not be able to integrate your function the way it's given to you. So you might say like, okay, fine, I got it set up, but I don't know how to integrate this. You'll have to switch your method anyway. Third, if you have a washer, you're going to find that shells are usually much easier to work with. If you have a disk, you're probably going to keep using the disk method from 6.2, but washers, you're probably going to use a shell. And if you're like, wait, washer, use a shell, the regions are going to look the same in 6.3 as they did in 6.2. It's just the method's different. So it'll still be a washer, but you can find the volume of the region using a different method. So let's get into that. 6.3 is the method of cylindrical shells. There were two things I was thinking about when I was yapping away at you. Now I need to remember what they were because I think they were important points. I need to write things down as I'm yapping. 6.3 is officially called volume of a solid of revolution cylindrical shells. We'll just say volume cylindrical shells. Okay. Oh, okay, so to sort of give you a little bit of a heads up as to where we're going after this, 6.3 is more of the same that you saw in 6.2 using a different method. However, we still won't be done with volume yet after tonight because we have 6.4, which is volume using cross sections. Even though it's a little bit of a departure from the volume that we're doing right now, it's the same sort of idea. I'm going to be starting your asynchronous lecture with 6.4. I'm not going to spend a ton of time on 6.4, however. I'm spending like a whole class period on 6.2 and 6.3. 6.4 is not going to take me a whole class period. It can be kind of challenging to work through the stuff in 6.4. However, there aren't a ton of really good exercises that are available to give you. And I should have just written my own separate homework set, and I waited until it was too late. So we're going to talk about it. I'm not going to put a whole ton of emphasis on it, but I will talk about that in the asynchronous lecture that I'm going to be recording probably tomorrow. If I try to do it tonight, I'm going to be too tired. Plus, it's good running weather tonight. You guys, it's going to be like 68. I'm going to have to go for my run. I won't be able to do that and then come back and record a lecture. It'll be like 2 in the morning. It's not going to happen. And then I'll probably start getting into arc links in the asynchronous lecture. And then maybe next Wednesday, I'll pick up on some surface area stuff from 6.5. But we will be wrapping this up. And if I'm looking at when we are scheduled to take our first exam, oh, here's my syllabus. Let's see how on track we are, because I said that the first exam was probably going to be 1 that would be most likely to move. Let's see. The week of 8:30, that's this week. I don't know. Let's see how we're doing next week, because I mean, we might be on target for that, but we might just have to start chapter. If we end up moving test 1, we'll have to start chapter 7 first. But as of right now, let's keep it planned for 9:15 and kind of see how things go. We'll see. We can always reevaluate. Okay, I'm going to give you some formulas here for the method of cylindrical shells. If you're really interested in seeing why this method works, you may feel free to look at the pictures in your book. I'll draw you some pictures so that you can sort of get an idea. I'm going to give you some formulas that are slightly different in notation than the formulas in your book. The ones in your book, I don't care for the way they're written. Your book tends to write things in really general terms, and then they just assume that you're going to make necessary changes to the functions. And sometimes students don't realize they need to if the formula is written in a general term. So I'm going to write these in the way that I have always taught them. Here are your formulas for finding volume using the method of cylindrical shells. And I'm going to put some pictures along with these so you get an idea of what's going on here. If you are looking at a horizontal axis of revolution, your volume is going to be, and here's one difference. It's not going to be pi, it's going to be 2 pi. Here's another big difference. We're going from C to D. When we go from C to D, you should be thinking dy integral. That's just the way the notation works. And that is indeed what we are going to be doing. So you're going to take this function p of y and multiply it by another function h of y and integrate with respect to y. P of y, well, let me give you a picture first, and then I'll tell you what P of y is. So the picture you're looking at could be something like this. And let's say maybe you have a curve that looks something like that. One big difference I had mentioned, we were talking about rectangles. When you're talking about using a method of cylindrical shells, we're going to be drawing rectangles that are parallel to the axis of revolution. In this case, we have a horizontal axis of revolution. So we are revolving. I'm just going to put it around the x-axis right now. That could move, but right now I'll just put it there just for a general picture. And your rectangle, we're going to draw parallel, not perpendicular to the axis of revolution. So in 6.2, we drew our rectangles perpendicular. In 6.3, when we use shells, we're drawing them parallel. Now, P of y is going to be the distance from the center of the rectangle to the axis of revolution. So P of y is the distance from the center of the rectangle to the axis of revolution, AOR. Now, this is just some distance. It kind of depends on where your axis of revolution is. But if I was talking about an axis of revolution that was the x-axis, for instance, then P of y would just be y, because your rectangle is going to be y units away from the x-axis. And imagine if you're moving this rectangle up or down, it's always going to be y units away from the x-axis. So if you want to make a note here to yourself, if the axis of revolution is the x-axis, then P of y is always going to be equal to y. The only time that's going to change is if we end up moving the axis of revolution to some other line that's in the form maybe of like y equals b, where b is some constant. If our axis of revolution is y equals b, where b is some constant, then we would say that P of y is just going to be b minus y. Now, h of y is going to be the height of the rectangle. This is sort of where your function comes in, just the same way that you took the height of the rectangle in 6.2. So h of y is the height of the rectangle. And P of y is the distance from the center of the rectangle to the axis of revolution. Okay, now h of y is dependent on your function. So whatever that function would be, the height of your rectangle is kind of dependent on the value of y that you're sitting on. So if I were to move this rectangle up, obviously the rectangle would get shorter. And if I were to move this rectangle down, in this case, assuming that the rectangle is, of course, as tall as your region, if I were to move the rectangle down, then the rectangle will get taller. So that's going to be controlled just by whatever your function is. And like I said, if you're interested to see how they derive these formulas, feel free to look in your book. But basically, it's like you're just taking this slice through your region, and as you revolve it, you're just making these cylinders with it, and what you're doing is just varying the width of that rectangle, and just sort of building this cylinder that sort of revolves around the axis. There are pictures of this in your text. I mean, I'll pop one up here, but this one is, of course, I picked one that had to be a vertical axis of revolution. Let me find a horizontal one. I'm looking at page 451, but basically you're just taking this slice, and as you revolve it around, you're creating these cylinders, and as you vary the width of the rectangle, that's accounted for in the dx or the dy, kind of depending on what integral you're using. In this case, it'll be a dy. But that's kind of why shells work the way they do. Feel free, though, to kind of look at the pictures if you want. They've really dissected a lot of that. And we've kind of pulled this apart. Now you can really apply this also to a vertical axis of revolution. And it's going to work the same way. In this case, though, the volume is going to be 2 pi times the integral from a to b, and we're going to take p of x times h of x dx. And same idea, though. P of x is going to be the distance from the center of the rectangle, and in this case, to your axis of revolution, which is going to be vertical. So your picture, I mean, you could have the same region even, but maybe you could talk about finding the volume as you revolve that region about the y-axis instead of the x, or any sort of vertical axis. Maybe it looks like this. Your rectangle is always going to be parallel to the axis of revolution. And same idea here with p of x as with p of y. You're looking at the distance from the center of the rectangle, right to left, to the axis of revolution. So no matter where you move this rectangle, as you slide it to the left or slide it to the right, you're always going to be x units away if your axis of revolution is the y-axis. And then, of course, the height of your rectangle just depends on what your function is. Y equals f of x. And same idea here. If the axis of revolution is the y-axis, then p of x is going to be equal to x. If your axis of revolution is x equals a, then p of x will be a minus x. So I'm going to show you some examples of how to use this. Sometimes students find this to be easier than discs and washers, and they'll use this all the time as long as they can integrate the function. Sometimes it's the opposite. When I was a student, I always preferred discs and washers, but I think it's because I'm very stubborn and I learned that first. And then once new information came, I was very, very like, nope, not accepting this. So be open and receptive to the method of cylindrical shells. You might find that you really like it. Like I said, especially when it comes to washers, it's easier to find the volume using a shell, which I'm going to show you in the first example. Before I get into that, are there any questions on this definition? Wonderful. Okay, then. Example 1. So this is actually going to look kind of similar to your quiz question. Find the area. Oh, let me give you the info first. Okay, so we're going to do a couple different things with this. First of all, we're looking at the region y equals the square root of x, y equals 0, and this time we'll be nice and give you x equals 4, which is a perfect square, instead of x equals 3 like you saw in your quiz, even though it really wasn't that big of a deal. So this is what we're going to be using, and I'm going to give you 4 parts here. So you can kind of see how the shell method works depending on where you move your axis of revolution. And then we'll talk about a couple of different types of examples and how you would do that using shells. All right, so A is going to be find the volume when the region is revolved about the y-axis. Now, even though I'm going to be using the same function for all 4 parts, I didn't want to just do a general drawing and keep referring back to it because we're probably going to keep manipulating the drawing, and I'm going to probably just re-sketch it each time. It's a pretty quick sketch, and you've already seen it a couple of times today. So this is y equals the square root of x. And we're looking at this between the x-axis and x equals 4. And of course, when x is 4, y is the square root of x. So y is the square root of 4, which is 2. Okay, so there's your region. Now, first, we're going to be revolving this about the y-axis. So right off the bat, notice that this would have been a washer. You're going to find that this is going to be a lot easier to work with when we are using the method of cylindrical shells. First of all, when we're working with shells, make sure that you're drawing your rectangle parallel to the axis of revolution. Honestly, I feel like it's kind of essential here to draw the rectangle. I can't force you to do it, but I think it really helps. All right, so the difference here with shells is that when you're talking about a vertical axis of revolution, you're switching over to rewriting everything in terms of x instead of y. So we're going to be looking at using the formula 2 pi times the integral from a to b of p of x times h of x dx. And what we need to do here is just find these 2 functions p and h. And once we find them, we'll multiply them together and we'll integrate. Now, I had already mentioned that if your axis of revolution is the y-axis, then p of x is x. But it's always important to remember the definition of p of x instead of just writing down something that's meaningless. So the distance between your rectangle and the axis of revolution is always going to be x units. Whether you want to think about this right to left, left to right, don't care, it doesn't matter. Just it's some distance between the axis of revolution and your rectangle. Now, no matter where you scoot this rectangle, you could slide it all the way over. But imagine if you took your rectangle and you slid it all the way to the end of your region at x equals 4, it would be 4 units away. It would always be x units away no matter where you put it. You could always slide your rectangle all the way to the left so it meets the axis of revolution, in which case x would be 0, the distance would be 0. So no matter where you put this, the distance from the rectangle to the axis of revolution is going to be x units. Okay, so we have p of x equals x. Now, the height of the rectangle is going to be controlled by this function, y equals the square root of x. So wherever you put the rectangle, if you put it at 0, the height of the rectangle is going to be the square root of 0, which is 0. If you slide your rectangle over to 4, the height of the rectangle will be the square root of 4, which is 2. So it's always going to be controlled by this function, square root of x. So the height of your rectangle is the square root of x. Questions so far? Now it is up to you.
Is h of x always going to be just your function?
It kind of depends on where your axis of revolution is. So I don't want to say always, but trying to I hate when students ask me, like, is this always going to be the case? It's usually going to be the case unless you have some funky figure. Or I'm going to show you an example in a few minutes where your region's controlled by two functions. So you're going to kind of see how that's going to change. But or like, for instance, if let's come back to this question, because you're going to see some ways in which it will not necessarily be the function, in which you're going to have to just make a slight adjustment to it, depending on where your axis of revolution is. And I don't want to say if your axis of revolution is one of the main axes that that's always going to be the case, because of what I'm going to do in example 2. But let's come back to this question, because I think it's going to be answered by the rest of the example. Sorry for the non-answer. I don't even know who asked me that question.
That was me.
Oh, it was Joseph. Okay, also known as Joe. Okay, let's come back to that. All right, so it's kind of up to you whether you want to multiply p and h right now, or if you want to put them into your integral first. I'm just going to go ahead and multiply p times h, x times the square root of x. Now, since you're going to have to integrate this, you're going to want to simplify this so that you have a rational exponent, something that you can integrate. So remember that the square root of x is x to the 1/2 power. And when you're multiplying and you have the same base, you add the exponents. So 1 plus 1/2 is 3/2. And now we can go ahead and set up the rest of the integral. So we're looking at a volume of, don't forget you have 2 pi. We're going from x equals 0 to the leftmost edge of the region to x equals 4, which is the rightmost edge of the region. The integrand is going to be x to the 3/2 and dx. So again, you're looking at a washer, and you did not have to think about what's the outer radius, what's the inner radius, right minus left, which one's which, I don't know. With shells, this is going to be easier for you. And then you'll just integrate. So you have 2 pi times 2/5 times x to the 5/2 from 0 to 4. And then you'll just use the FTC. And you'll get 4 to the 5/2 minus 0 to the 5/2. 4 to the 5/2 is 4 squared times the square root of 4. So 4/5 pi times 16 times 2. 32 times 2 is 64 times 2 is 128 fifths pi. Okay. I do my shift. Questions on example A? Okay, so let's switch this up for B, and we'll do a disk, and we'll revolve this about the x-axis. Now, personally, I think that the disk method is usually easiest anytime you have a disk, but I want to show you how to use the method of cylindrical shells for this particular situation. Here's your region. We're looking at the point 4, 2, and we're going to take this region and revolve it about the x-axis. We're going to draw our rectangle parallel to the axis of revolution. Now, the reason I think it's so important to draw your rectangle is because it's really going to help you see here what the height of the rectangle is. It's going to be hard to see if you don't draw it out. All right, so remember, we're switching this out here for a horizontal axis of revolution. When we're using the method of cylindrical shells, we're going to be looking at everything in terms of y. So I'm going to be taking 2 pi times the integral from c to d of p of y times h of y dy. And if you ever can't remember which one's which, as long as you remember to draw your rectangle parallel to the axis of revolution, then you'll know that, oh, if my p of x, if you got it wrong, has to be the distance between the axis of revolution and the rectangle, well, it's y units, therefore it must be p of y. Therefore, I know I must be using a dy integral in this case. So we're talking about revolving about the x-axis. I already told you that p of y in that case is going to be y. No matter where you move your rectangle, it's always going to be y units away from the x-axis. So we'll have p of y equals y. And then the only trick here, as far as finding the height of the rectangle, is you have to remember that we are talking about going right minus left. So in this case, and I think this is kind of what I was thinking about when Joe was asking his question about the height of the rectangle always being the function value, because in this case, it's not. And by the way, we do need to rewrite this function as x equals y squared, but the height h of y is not actually y squared in this case, because remember, we need to take right minus left. The height of your rectangle is going to be 4 minus y squared. Now, I'll tell you what I did as a student, and I still sometimes do it as an instructor. I check this. I think about like, okay, well, what if y is this? What if y is that? Does my h of y make sense for the height of the rectangle? So for instance, I say, let's let y be 2. If I let y be 2, that means I'm looking at what happens to the height of the rectangle if y is 2. Well, if y is 2, I'm sliding the rectangle all the way up to the top of the region. And notice that as it slides along, it's going to get smaller and smaller and smaller and smaller and smaller. Well, if y is equal to 2, 4 minus 2 squared is 0. Indeed, the height of my rectangle would be 0. Now, if I were to instead slide this all the way down, in that case, I would be letting y equals 0 because I'd be sliding my rectangle down to y equals 0. Well, h of 0 would be 4 minus 0, which is 4. And my rectangle would indeed be 4 units long. So you can just do some, quick mental checks there to make sure that the height of your rectangle actually matches what the function says it's supposed to do. You could even say, okay, well, what happens at y equals 1? What if I put this rectangle exactly in the middle? Well, if y is 1, 4 minus 1 is 3, then yeah, it does look like your rectangle would be 3 units long, so on and so forth. So that's kind of the way I would do a mental check to make sure that my answer made sense. Because if you just said h of y is y squared, well, that wouldn't check out, because then if y is 0, you'd be sitting here at the bottom, and 0 squared is 0, and you'd be like, wait a second, the height of my rectangle is not 0. Something is wrong. Okay. Any questions on P or H? Okay. So let's multiply these two together. P times H is y times 4 minus y squared. Since we're going to integrate, we want to go ahead and have this expanded out, because remember, we don't have a product rule for integration. So we have 4y minus y cubed. And then we just need to set up the rest of our integral. So we're taking 2 pi times the integral from, and now I need y limits of integration here. So I'm going from y equals 0 up to y equals 2. That's the uppermost point of that region. And then we're looking at an integrand of 4y minus y cubed dy. And then you'll integrate. So 2 pi times 2y squared minus 1/4 y to the 4th from 0 to 2. If you want, you could factor something out, or you could just leave it. I'm just going to leave mine. 2 cubed is 8. 2 to the 4th is 16. Divided by 4 is 4. Minus 0 plus 0. And you get 2 pi times 4, which is 8 pi. I'll tell you another really cool thing about this section is you can double check this using your disk method. Any of these you could double check using the other method. The only problem that you might run into is that, let's say you were trying to double check your shells using a washer and you accidentally screwed up the radii for your washer. Maybe your shells were right, but you'll think they were wrong because you did it wrong with your washer. So, but if it's a disk, you might want to do a quick check just to make sure, because the disk method students usually find to be really accessible. So I'm going to say here, check using a disk, just because I want to bring all this back together. Okay, so now if you were using a disk, remember you would be drawing your rectangle perpendicular to the axis of revolution. So we're still revolving it about the x-axis, and if we're perpendicular to the axis of revolution, your rectangle would look like that. All right, so if we're checking using a disk, I have a horizontal axis of revolution. My volume is going to be pi times the integral from a to b of r of x squared dx. And because we know it's a disk, we don't need to worry about subtracting off that inner radius squared. It touches the axis of revolution at every point, hence it is a disk. R of x in this case would just be the radius. So go from your axis of revolution up to your function, which is y equals the square root of x. So r of x is the square root of x. So you can go ahead and set up your volume, pi. X is going from 0 to 4. R squared is then x dx. So slightly easier to do this using methods from 6.2. So let's see, 1/2 x squared from 0 to 4, pi times 1/2, 4 squared is 16, is indeed 8 pi. If I were you, I would work a lot interchangeably between these two methods. Otherwise, you're going to get stuck on one and you're going to forget the other one. Go back and forth. Train your brain. And as you're trying to prepare for your exam, my suggestion always is to do these problems using both methods and see if you can get the same answer using a different method, as long as you know what the answer is. So on your homework, let's say you get the answer right, go back and do it the other way and make sure you can match that. I think that would be the best thing for you. I know what's good for you. I do. It's true. When it comes to math anyway. Questions on B? Okay. Let's work on C. And we are going to take the same region and we're going to revolve it about the line x equals 5. So again, I'm just going to do a quick sketch of the function. Maybe we'll look at what happens here at 4, cut it off there, and then we'll put 5 right about here. And revolve it around. All right, we're using shells. Notice that if you were using methods from 6.2, this would be a washer. So this might be one where you would try to do it with a shell first, unless you couldn't integrate it, because a washer is always going to be easier if you try to use a shell. Draw your rectangle parallel to the axis of revolution. Okay, so I have a vertical axis of revolution, which if I was using methods from 6.2 would mean that I needed a dy integral. However, for shells, I need a dx integral. So the two things I need to find here are p of x and h of x. So p of x is going to be the distance from the center of the rectangle to the axis of revolution. Now, if my axis of revolution was the y-axis, then p of x would just be x. I would just be looking at x units. But I gave you in your definition that if your axis of revolution is x equals a, then p of x is a minus x. That's what we're going to use here. So I'm going to plop that down, and then we're going to talk about why that's the case. And again, you're thinking right minus left. So p of x is going to be the distance from your axis of revolution to the center of the rectangle, and it's not x units, it's 5 minus x units. I have to shift that over to where the axis of revolution is. But again, you can test this out. You can let your rectangle sit at whatever x value you want it to sit at. So let's say that I wanted to move my rectangle over to 4. Great. If x equals 4, 5 minus 4 is 1. My rectangle would indeed be 1 unit away from the axis of revolution. If I wanted to scoot my rectangle all the way over here to 0, 5 minus 0 is 5. Yes, indeed, my rectangle would be 5 units away from the axis of revolution. So you can always pop in some numbers just to make sure that that makes sense, if you're not sure. H of x is just going to be the height of your rectangle, which in this case is going to be the square root of x. Now you're going to notice how this particular integral is going to be really similar to what you did for part A. The only difference is instead of just multiplying by x, you now have this binomial 5 minus x. But we're going to take p times h, and you're going to get the square root of x times 5 minus x. I'm going to rewrite this using rational exponents since I know we're going to have to integrate it anyway and use that power rule. So we're looking at 5x to the 1/2 minus x to the 3/2. So let's go ahead and set up the volume. We're taking 2 pi. X is going from 0 to 4. So remember here that you're only integrating where the region exists. Sometimes students get confused and they're like, well, should I go all the way up to 5 since my axis of revolution is at 5? No, only integrate where the region is. And the region is going from 0 to 4. That's not going to change just because your axis of revolution changed. And we're going to take 5x to the 1/2 minus x to the 3/2 dx. And then you will integrate and use the FTC. And I'm going through this part a little quickly because I feel like we should all be pretty good with this by now. I hope. So you have 2 pi on the outside. Use your power rule there and then simplify. And you should be getting, I'll just finish it out for you. Let's see, 10/3 times 4 times the square root of 4 minus 2/5 times 16 times the square root of 4. And then your lower limit at 0 in both cases is going to zero out. So you don't need to worry about that. All right, so 10/3, 8 minus 64/5. And you should come up with 416/15 pi. Probably check this if I have any battery life left. 80/3 minus 64/5 times 2. Yeah. Actually, I have the charger plugged in. There it is. All right, questions on C? Okay, let's do D. So for D, we're going to take the same region. We're going to do one more thing to it. We're going to revolve it about the line y = 4. Maybe we'll just set this one up and move on to the next one, since I feel like the setup is really the bread and butter here. The meat and potatoes, if you will. All right, so there's your region. You have a point at 4, 2. We're revolving this about the line y = 4. Remember, y equals is a horizontal line. If you didn't know that before, hopefully you know it really well by now. So we have a horizontal axis of revolution. And with shells, that means that we're looking at a dy integral. Got to switch it up for shells. 2 pi, we're going from C to D. P of y, h of y, dy. And some of you who spent the last several days struggling through your 6-2 homework might actually be really pleasantly surprised that they're so happy that they don't need to worry about finding inner and outer radii. draw your rectangle parallel to the axis of revolution. Now this looks pretty similar to what we did for B. So if you feel like, okay, I've got the height already, that's fine. We already talked about the height as being 4 minus your function, which is x equals y squared, right minus left. And then the only thing we need to consider here is P of y, which is the distance between the axis of revolution and your rectangle. So I gave you a note that said, if your axis of revolution is y equals b, then P of y is b minus y. So P of y is 4 minus y. And you can think about this even top minus bottom. 4 minus y units will get you down to your rectangle. And again, you can check it. Scoot your rectangle all the way down, and you're expecting this distance to be 4 units. Well, if it's all the way down, it's sitting at y equals 0. If y equals 0, 4 minus 0 is indeed 4 units. If you scooted your rectangle all the way up to the top of the region, you'd expect the distance between your rectangle and the axis of revolution to be 2 units. 4 minus 2 is indeed 2. So that will work for you. In this case, when you want to multiply h and p, you're just going to have to multiply out these 2 binomials. No big deal. Just FOIL them out. And you'll get 16 minus 4y minus 4y squared plus y cubed. And I'll set up this integral for you and then tell you what you're supposed to get. Remember, this is a dy, so all the little things here matter. On a dy integral, I'm looking for where our region goes as far as where we sit along the y-axis. So our region's going at its lowest point from 0 to its highest point at 2. So we'll integrate from 0 to 2. And then our integrand is just this function. I'm going to write mine in descending order, but it does not matter. And when you integrate this, you should get 104/3 pi. I'm going to do a different example using different functions. Are there any questions on this one before I move forward? I'll show you some different scenarios here. Example 2, find the volume when the region bound by y equals 1/3 x cubed and y equals 6x minus x squared is revolved about the line x equals 3. This is going to drive me crazy. Region bounded by. Okay, now last Wednesday, I told you that you can use Desmos to graph these, or you could use your graphing calculator. That is true still. And just like last Wednesday, I'm going to tell you that in chapter 7, you're going to need to know how to complete the square. So I'm going to do that again because I feel like it's going to be really beneficial to you as you work into these advanced integration techniques in 7.4 when you do. So I'm going to complete the square real quick to graph this. In order to complete the square, I want to have my lead coefficient be positive. First of all, I'm going to write this as negative x squared plus 6x. By the way, I'm not requiring that you do this on your homework or on the test. I just want to run through this because you're going to see it again later, and I don't want it to be a big shock to the system. I'm going to factor out the negative because I need the lead coefficient to be positive. And then I'm going to complete the square inside the parentheses. So I'm going to take half of the middle term's coefficient, which is -3, and square it, which is +9. However, if I want to add something inside the parentheses, I must account for that. So actually, I already did that over there. I don't need to worry about this side. I added in not just 9, but -9. So I technically subtracted 9 from both sides. So I need to do the same thing on the left-hand side. And then I'm going to rewrite this as y minus 9 is negative, and then I'm going to write my trinomial as a binomial squared. So I'm taking half of the middle term's coefficient inside the parentheses, and I'm going to square the quantity. So x minus 3 times x minus 3 does indeed give me x squared minus 6x plus 9. And the nice thing is now when I want to graph this, I can add 9 to both sides. And now I have this in vertex form. And yes, you could technically find the vertex by doing -b/2a, f of -b/2a, but you're going to have to complete the square in chapter 7. So you might as well just at least passively pay attention. So the vertex, remember this is a shift to the right 3 units. So the vertex is actually going to be at 3, 9. Remember, we're always taking the opposite of what that value is. When we subtract inside the parentheses, we're moving right. When we add inside the parentheses, we're moving left. Outside the parentheses, we keep the sign that's in front of it. And don't forget that a negative a means that your parabola is opening downward. So our vertex is at 3, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3, 9 is right about here. It opens downward. It's going to go 1 unit on each side. And then, notice that if x equals 0, you end up with y equals 0, just using those function values. So the general gist here is going to look like this. So this is technically y equals 6x minus x squared. Don't you feel like it's more satisfying when you graph it by hand versus just popping it into Desmos? I don't know. Seems like it to me. But maybe it's because I teach this skill in college algebra and I want to just bring it back so you feel like you didn't just learn it for nothing. All right, so there's that graph. The other one is this cubic function, 1/3 x cubed. To graph that, you might just want to plot some points. Oh, by the way, I wanted to label that as 3, 9. So for y equals 1/3 x cubed, if x is 0, y is 0. So we definitely have this intersection point. If x is 1, y is 1/3. So really small value here. If x is 2, well, 2 cubed is 8. Divide that by 3, and you get like 2.67 something. You can kind of start to put this together. If x is 3, 3 cubed is 27, divided by 3 is 9. That's excellent news for you because you have a point at 3,9 already. So now you can see that this is an intersection point between these two graphs. Now you should still be able to see that if you graph this on Desmos. I know, sorry, this looks like almost like it's going left, but it is not. It can't be because it is a function. You'll be able to sort of hover over the intersection and it'll tell you what the point is. But you could also check this in your graphing calculator, or you could always set these functions equal to each other and solve to find the intersections. Would anyone like to see that, or do you feel comfortable with the intersection point? Tell me if you want to see me find the intersections at 0 and 3. Yes or yes? No? No? Okay, that's fine. I'll let it be. It's technically an algebra technique, but so are so many of the things we need to practice in this class. Okay, so there's your region. We are revolving this about the line x equals 3. 1, 2, 3. And actually, that's right at the edge there. And we're going to draw our rectangle parallel to the axis of revolution. Going to look something like that. Find the volume when the region bounded by y equals 1/3 x cubed and 6x minus x squared is revolved about the line x equals 3. This is a vertical axis of revolution. When we're talking about using the method of cylindrical shells with a vertical axis of revolution, I need to make sure that I have a dx integral. So I'm going to look at 2 pi times the integral from a to b of p of x, h of x, dx. Okay, now p of x is not just going to be x in this case because I'm not revolving this about the y-axis, but I can use the fact that p of x is going to be b minus x as long as I'm revolving this about any line x equals b. So we're going to let p of x be 3 minus x. And again, you can always, test that out. Move x over here to 0. 3 minus 0 is 3. You're 3 units away. It works perfectly. But you can also use that formula, b minus x. H of x is going to be the height of your rectangle. Now, in this case, the height of the rectangle is going to be controlled by 2 functions, not 1, because we're not talking about smashing a function between one of your axes. We're talking about 2 curves. So you're going to go top minus bottom in this case. Your top function is the parabola. So you're going to take 6x minus x squared and subtract off the bottom function, 1/3 x cubed. Now, the only super obnoxious thing about this problem is not the work that we've done so far. It's just having to multiply out the binomial and the trinomial, and it's just algebra, and it's not even college algebra. It's like intermediate algebra, but it's tedious, and if something goes wrong, your whole problem's going to go wrong, and your integral is going to be off, and you're going to be banging your head wondering, what the heck did I do wrong? And it might just be that you accidentally mismultiplied your binomial and trinomial. So it's tedious. That's all I can say. But you're going to multiply them out. You're going to take P times H. I like to put the binomial in front of the trinomial, but that's up to you. 3 minus x. I usually like to have these in descending order too. You know what? I am going to write these in descending order. Then it's going to allow me to do this vertically. Instead of writing 3x, I'm going to go negative x plus 3. And I'm going to write the second factor in descending order also. So let's multiply. I'm going to start by multiplying the negative x. And we're going to be very careful here to make sure that we do this correctly. Before I proceed, are there questions? This class isn't very question heavy, which is okay if you're just taking it all in. Or maybe I'm doing such a good job explaining it that there just aren't any questions. There's always that possibility, but I don't know. All right. Well, negative times a negative gives us a positive, and then plus x cubed, and then minus 6x squared, negative x cubed, negative 3x squared, positive 18x. Oh, wait, I already got everything. I don't know why I was thinking trinomial into a trinomial. Because it was not, right? 1, 2, 3, 1, 2, 3. All right. Negative 9x squared plus 18x. You know, just be careful with your signs. Leave this here for now. And then you'll pop that into your integral. 2 pi times the integral from, well, look at your region. Remember, you have a dx integral. X is covered all the way from 0 to 3. So the region exists between 0 and 3. That's where you're going to take your integral. So 0 to 3 of p times h, which is 1/3 x to the 4th minus 9x squared plus 18x dx. Equals 162/5 pi. You can work that out. I don't really feel that that is the best use of our time. Okay. So I had mentioned at the beginning of this problem. Actually, I mentioned it at the beginning of our quiz problem, I want to say. We were looking at something like this. I want to say it was 4x minus x squared. I don't know where it is now. Either way, my comment that I made at the time, oh yeah, it was the quiz question number 1, 4x minus x squared, was like, well, let's say you tried to do this instead using right minus left. How would you even do that? Because you would have to solve for x. One way that you could do that, if you were just really resistant to using a shell, is to use the form where you completed the square. It could still be done, and I guess I feel like it's pertinent to point that out because I don't want you to feel completely stuck using one method or another. But if you were going to use a washer, I'm not going to do the whole thing, but I kind of want to give you a little bit of a roadmap here. We rewrote the function as y equals negative x minus 3 squared plus 9. That was what we did. We said this was also equal to 6x minus x squared. Okay, so those are the same thing. If you were going to use a washer, you still have a situation where you have a vertical axis of revolution. For a washer, you would need a dy integral, not a dx integral. you could still do it. You would just need to solve this equation for x. So if you were going to do that, you would need a dy integral, and you would need to solve the equations for x. You could still do it. You would just have to make sure that you knew which part of the equation you were using. But you can get x by itself by subtracting 9 from both sides. And you'd have to have it in this form in order to do this, by the way. Divide out 1 on both sides. So to divide by 1, you can just switch the order of the subtraction. Divide each term by 1, just change the signs. And then use the square root property to get x minus 3 out of that square. So undo the square by taking the square root on both sides. When you take the square root on both sides, you must apply a plus or minus. And then to solve this for x, you're going to add 3 on both sides. And then you need to know which one's which. That, if you'd like, you can check using Desmos. The nice thing about Desmos is you can actually graph an x equals function, and it will graph it for you. It's not actually a function because it's an x equals. But what you would end up getting here is that the positive side of this would be 3 plus the square root of 9 minus y. And then the left-hand side would be x equals 3 minus the square root of 9 minus y. This would be very, very messy as a washer, but it could be done. So if you're very stubborn and you want to check it and you want to do it both ways, I sometimes have students who are like, I just want to know, I just want to do it, just show me how to do it. This is the way that you would have to do this. And you could then figure out the outer radius, taking 3 minus the square root of 9 minus y. I'll actually write that down. Outer radius would be 3, right minus left, minus, and then this quantity, 3 minus the square root of 9 minus y. And then your inner radius, similarly, would be 3 minus, and then this inside piece right here, where you have that empty space occurring. So that would be controlled by this function. 3y equals x cubed, and x is the cubed root of 3y. So you'd have 3 minus the cubed root of the quantity 3y. And then, you'd have to simplify those and square them. If you really want to, it would not surprise me if someone emailed me and said, hey, does this look right, or where did I go wrong? I know how you Calc 2 students are, but if you never want to look at this example again, that's also fine. I did want to set up one more for you just because it was slightly different in that the axis of revolution was negative. So I'm going to do that setup for you real quick, and then we'll call it a day. But I mean, pretty much we've exhausted everything else that we could have done today with shells. Before I do that last example, are there questions on this one, example 2? A, B, C, D. Okay. So the last one that I thought might be good to do is example 3. Find the volume of the region I should say find the volume when the region bounded by the x-axis and y equals 3x minus x squared is revolved about the vertical line x equals -1. I just did one extremely similar to this that we did by completing the square. If you want to pop this one into Desmos, be my guest. It is y equals, I'm just doing mine separately, 3x minus x squared. You could also do this in your calculator. Oh, you know what I was going to mention too? I thought about this at the beginning of class. I don't know how much you've played around with Desmos, but if you wanted to enter certain functions, there is a symbol palette for that, but also like a square root, you could enter like SQ, RT, and then it just pops up automatically. So if you're graphing square root functions, you could do that. But there's also like a template, which I'm assuming you use. But I know sometimes it's easier to use the shorthand, like the caret when it's squared, so on and so forth. Okay, so you end up getting this function that looks kind of like, let's see, it comes down here at 3. It's a parabola, and it goes a little bit over 2 at the vertex. Kind of like that. And we are bound by this parabola and the x-axis. So there's your region. And we are revolving this about the vertical line x equals -1. Okay. So in this case, let's talk about what we're actually looking at here. A vertical axis of revolution, which in our case, and if you want to draw your rectangle, it'd probably be a good idea. When we're using a shell, a vertical axis of revolution means we're looking at dx. This is kind of why I don't know if I want to go with your formula in this case, because remember we're thinking about P of x as being the distance from the center of the rectangle to the axis of revolution. Now, if I was looking at an axis of revolution that was the y-axis, then I would be looking at P of x as x because I'd be x units away. However, as I move that in the opposite direction of the y-axis, well, I'm just adding units to that. So instead of being x units away, now I'm talking about x plus an additional unit away. So in this case, when we're moving to an axis of revolution that's negative, you are going to want to add that on instead of subtracting it from your value, or subtracting your value of x from it. So your P of x is x units up to the y-axis, and then you're going to add an additional 1 unit. So there's the x, here's the 1. So I think looking at this visually kind of helps you to understand why that distance would change in that way. But we would say that P of x is this distance x plus 1 more unit. And then your h of x would still just be the height of your rectangle, 3x minus x squared.
So if it was at x equals -2, then we'd add +2.
Yeah.
Okay.
So, yeah, so let's add a little, you might want to add a little note here. Assuming the axis of revolution is right of the region, which most of the time it is. It's pretty rare that you're going to get one that moves the opposite direction. But you could say the same thing in this instance for P of y. This assumes that your axis of revolution is going to be above when it could possibly be below. So if your rectangle is to the right, then you're going to have to switch that up. Which is kind of why I wanted to show you this instance. And like I said, you're not going to see that very often, but if it does come up, I want to make sure that we understand how to find P of x. Okay. And of course your region's going from 0 to 3. So if you want me to finish the setup here, you're going from 0 to 3 of x plus 1 times 3x minus x squared dx. Okay, I already put some homework up for you for 6.3. The 6.2 homework is set to be due Friday. So anything asynchronous, I'm just going to have to do Fridays. I'm going to put up an asynchronous lecture that covers 6.4 and maybe the start of 6.5 by Friday morning. So I'll probably record it Thursday. I really don't think I'm going to get to it tonight. But I'll probably record it Thursday and put that up for you by Friday so that you can get started right away. Some of you are really fast and others like need a little bit more time to get going. But I would try to watch it at some point this weekend by Monday at the latest, at the absolute latest, because you don't want to fall behind. And some of you are already behind. So let's get in gear. I know it's hard to get started and sometimes I feel like you're trudging through the mud, but you gotta get going on it. I'm going to be on my office hour for another 20 minutes, but if you want to go ahead and start the homework or work on your 6.2 homework, I'll be sitting here. If you have questions, you can let me know, and I'll email you over the weekend so you know your video is up. But if sometimes I post it and then I don't send an email because it's still processing, and I'm like, well, I don't want to email them and have them check and it's not ready yet. So feel free to go on and check D2L. Set up your notifications so you get a notification when a new YouTube video is posted. You could do that too. Or you could subscribe to my YouTube page and then you could see when I update it. So other than that, I'm done. Have a wonderful evening. I'll be on for 20 more minutes. And I'll see you next Wednesday. Good night.
Have a nice evening.
You too. Thank you. Last time I regretted not recording, so I'm going to let it go for a minute and see if anything super pertinent pops up.
Have a good night.
You too, Burfin.
Thank you.